let's take a look at electric and magnetic field applications. The first application we're going to look at is a charge accelerating in a uniform electric field in one dimension. And the setup we're going to have here is we're going to have two plates, potential difference V across them, distance D between the plates. And I'm just going to drop a little positive charge here. Maybe it's a little proton. Put it next to this positively charged plate. We're going to say that that little particle right there has charge Q, mass M, and make it start at rest. So if we just look at this and think about what would happen, well, that charge is going to accelerate to the right. Yeah, it's going to feel a big force to the right because there's an electric field. The electric field is going to cause an electric force. The force is going to cause it to accelerate. So it's going to zoom off to the right. And we have a lot of sort of instruments that we can use on this, a lot of mathematical relationships that we can use to describe this situation. First, we can say the electric field is equal to the potential difference across the plates divided by the distance between the plates. Also, the electric field is equal to the electric force divided by the charge on this thing. And if we say that this is a very small particle, of course, we can ignore the gravitational force on it, right? If it's a very, very small mass, gravitational force is negligible, and we can leave that out. So then the net force is equal to the electric force. It's the same as the electric force. And the net force is equal to ma, of course. So now, if we know the potential difference between the plates, and we know the distance between the plates, we know the mass of this thing, we know the charge on this thing, we can figure out the acceleration of the thing. And once we know the acceleration, well, we know the initial velocity. And let's say it's going to zoom to the other plate, then we know its displacement. Then we can use a bunch of kinematic equations. Also, if we think about energy, let's see, it gained kinetic energy. Figure that out. Figure out how much kinetic energy it gained. And if it gained kinetic energy, that means work was done on it. Also, if it increased its velocity, then momentum was added to this thing, which means an impulse was applied. A lot of those old ideas from mechanics we can still apply in this new situation with electric fields. All right. The second situation we're going to look at, second application, is a charge in a uniform electric field moving in two dimensions. So the setup here is we've got two plates, but we're going to orient them this way. And we're going to have a positive charge that's sent into the field this way. And, well, let's see. If it starts out moving horizontally, it's going to feel a force in the direction of the electric field, which is downward here. So it's going to feel a force downward. Well, let's see. Electric field is equal to the force per charge. If we can ignore the gravitational force, then the only force is acting on it is the electric force downward. So the acceleration is downward. The charge is also moving horizontally initially. So what we can do is we can separate the motion in x and y. The acceleration is vertical. There's only acceleration in the vertical. The horizontal acceleration is 0. So its velocity horizontally is going to be constant. It's not accelerating horizontally. Its velocity horizontally will be constant. It's only accelerating in the vertical direction. Well, hey, that's projectile motion. It's accelerating in the vertical direction. Its velocity is constant in the horizontal direction. It's going to have a parabolic trajectory. All of those structures that we learned to deal with projectile motion, we can now apply to this situation. The acceleration is not going to be 9.8 meters per second squared downward, like it was in regular old projectile motion. It's going to be some different acceleration that we can determine using the electric force and the net force equals ma. But it's the same concept, and we approach it the same way. The third application we're going to look at is forces between currents. So let's say that we have wires that carry currents to the left. Here's current 1, here's current 2. And I want to think about the magnetic field created by current 1. So the magnetic field created by current 1, well, we use our right-hand rule, do that. Magnetic field on this side will be out of the page. Magnetic field on that side will be into the page. So what that means is current 1 creates a magnetic field, and current 2 is traveling through current 1's magnetic field. So because current 2 travels through a magnetic field, well, a current traveling through a magnetic field will experience a force. So we use our other right-hand rule to figure out the force on current 2. And the force on current 2 would be in this direction. All right. So again, just to clarify, that is the direction of the force on current 2 by the magnetic field that was created by current 1. All right. Now, current 2 is also creating a magnetic field. The magnetic field created by current 2 is like this. Use our right-hand rule. Okay, there's the magnetic field created by current 2 up here, magnetic field created by current 2 down here. So current 1 travels through current 2's magnetic field. And so current 1 will feel a force. And the force that's felt by current 1, use our right-hand rule, is in this direction. All right, so again, that is the force felt by current 1 due to the fact that it moves through a magnetic field that was created by current 2. And you can see, when the wires are carrying currents that are parallel, there's an attractive force between those two currents, between those two wires carrying the currents. And we could do an example where the currents are in opposite directions. Try to figure out what happens. I'll leave that up to you. But you can see that in that situation, if they're in opposite directions, the force would be repelling the two wires. And, fun fact, there is an equation to describe the amount of force that's felt by these wires in these situations. The force per length on a wire that's near another wire is equal to mu 0 I1, I2 over 2 pi r, where mu 0 is the permeability of free space. We briefly saw the permittivity of free space before. This is the permeability of free space, which is just a constant. And then I1, I2, those are the two currents, and then 2 pi r. R is the distance between the parallel wires. Now, we could solve this, or we could derive this, but it would take quite a while, and it's not going to be the focus of this class. Application number 4 is going to be a charge moving in a uniform magnetic field. So let's say we have a magnetic field that's out of the page. We have a positive charge it's moving in this direction. If we use the right-hand rule, we can determine that the force is going to be in that direction. Well, let's think about what happens after that. If the force is perpendicular to the velocity, then it's going to deflect, and so it's going to move in that direction a short bit later. But at that moment, then, the force is going to be in this direction, which means that if we wait a little bit, it's going to deflect, travel in this direction. Okay, well, now the velocity is there, force is there, and if we continue the pattern, what you notice is it starts to move in a circular path. The magnetic force is always perpendicular to the velocity here, and if the force is perpendicular to the velocity, that's the recipe for circular motion. The charge travels in a circular path within a magnetic field if the velocity is perpendicular to the magnetic field. Here the magnetic force is the centripetal force, so that's great. We can write this down. We can say that QVB sine theta is equal to mv squared over r. And if the angle between the velocity and the magnetic field is 90 degrees, then great. Sine of 90 degrees is equal to 1, so QVB is equal to mv squared over r. QB is equal to mv over r. And we can write this down. Q over m is equal to v over br. Now the reason why that's useful is kind of a historical oddity. In 1897, J.J. Thomson, famous scientist, sent these things called cathode rays through a magnetic field. Now, cathode rays were these mysterious things. They didn't know exactly what they were, and that had been discovered about 40 years beforehand. So he sends these cathode rays through a magnetic field, and he was able to measure the velocity of the cathode rays. He was able to measure the magnitude of the magnetic field, and he was able to measure the radius of the path that they were traveling through. And so he was able to measure the charge to mass ratio of these cathode rays, the Q divided by the M, charge to mass ratio. When he did that, he could show that all of the cathode rays had the same charge to mass ratio, no matter what their velocity was, no matter what the magnetic field he sent it through. He could find that they always had the same charge to mass ratio. That was proof that he had discovered that cathode rays were made out of something that always was the same. Some particle that was always the same charge and always the same mass. And he called it a corpuscle. Cool name. But it turned out what he had discovered was the electron. He had discovered the electron by discovering its charge to mass ratio. And that's one reason why this is such a big deal. Now, if the magnetic field is not perpendicular to the velocity, then the charge will move in a helix, like this. We call it a helix, you might call it like a spiral, but fancy name is a helix. And application number 5, the velocity selector. So here we're going to have an electric field and a magnetic field brought together. So here's the setup. We have 2 charged plates, positive, negative, and we're going to send a positive charge horizontally between them. So, okay, there's an electric field, and so if there's an electric field, positive charge moves through it, it's going to experience an electric force in that direction, sure. But what we want is we're going to get this positive charge to travel in a straight line. And in order for that to happen, there needs to be another force opposite the electric force. So we're going to set up a magnetic field that somehow is going to do that. So let's think about how we would do it. Well, if we want this to travel in a straight line, we need a magnetic force that's upward. It's traveling directly to the right. We want a magnetic force towards the top of the screen. So if we use our right-hand rule, that means that the magnetic field would have to be into the page. All right. So in this situation, the electric force is balancing the magnetic force. So we can set up an equation. The electric force equals the magnetic force. So electric force is equal to Q times E. And that has to equal QVB sine theta. Now we're going to assume that the velocity and the magnetic field are perpendicular, so that the angle here is 90 degrees and the sine of 90 degrees is 1. That simplifies things. So we get QE is equal to QVB. We cancel out the Q's. Solve for V. So V is equal to E over B. This particle will travel in a straight line only if the velocity of the particle is equal to the electric field strength divided by the magnetic field strength. If the velocity is different than that, then the particle will not travel in a straight line. And we can explore that a little bit further. But this is called a velocity selector because only charged particles with the right velocity, the exact right velocity, will travel in a straight line through the velocity selector.